patent and 10 registered copyright. He also serves as an associate editor of International Journal of Engineering Research and Applied Sciences and is a recognized PhD supervisor in physics at RTM Nagpur University, Nagpur. Additionally, he is a reviewer for reputed journals such as Ceramic International, Polymers, and the Journey of Alloys and Compounds. Dr. Ganveer is an active member of several professional bodies including IAPT, STMI, and ISTE, contributing actively to the advancement of science and engineering education. We warmly welcome Dr. Ganveer and look forward to his valuable insights and inspiring interaction during this workshop. Over to Dr. Bhakti, convener.
Thank you, ma'am. So we are really privileged to have you, Dr. Vikrant Ganveer, with us. So I would like to invite our chairperson of the day, Dr. Vikrant Ganveer, to please introduce to the August gathering our today's speaker, today's resource person, Dr. Amol Nande. So Vikrant sir, please do the formalities.
Thank you, ma'am. Thank you. Good evening. On the behalf of organizers of National Workshop on Advanced Computational Tools for Physical Science, I warmly welcome you to this second day sessions. This workshop, organized under the banner of IAPT, is dedicated to exploring cutting-edge computational methods that are transforming research in physical science. It is my privilege to chair this session, which will focus on the exciting frontiers, computational luminescence. We are honored to have with us Dr. Amol Nande, working as Assistant Professor at Department of Physics, Guru Nanak College of Science, Ballarpur, since 2016. He is having dual PhD holders, University of Canterbury, New Zealand, and RTM Nagpur University. Postdoctoral researchers, IIT Guwahati, research in spintronics, nanoparticles, memory devices. He is also former research scholar of IIT Bombay, specialization in magnetotransport and multilayer thin films. He has published more than 53 research papers in international journals and conferences. He is also author of 7 books, including Elsewhere, 15 book chapters in Springer's Elsewhere Ville, 2 national patents published by Government of India. He is also the recipient of prestigious fellowships like Marsden Fellowships, CSR UGC NET qualified, JEST All India Rank 12, and GATE qualified All India Rank 351. He is also executive member of IAPT Vidarbha, IAQC members and research coordinator, and also PhD coursework lecturer in research methodology. I hope his work bridges theory and applications, offering insight into how computational tools can unravel the complexities of luminescence material and processes. Luminescence, as we know, plays a vital role in diverse areas from advanced material and photonics to medical imaging and energy-efficient lighting. Computational approaches allow us to predict, simulate, and design luminescence systems with remarkable precision. Today's lecture will definitely provide us with a deeper understanding of these computational techniques and their impact on physical science. Without further delay, I invite Dr. Amol Nande sir to deliver the lecture on computational luminescence. Please join me in virtual welcoming with a round of applause. Thank you. Please, sir.
Thank you very much, sir, for such a warm welcome. I hope, am I audible?
Yes, yes.
Could you please give me access to share my screen?
Yes, given, sir.
Oh. My screen is visible?
Yes.
Yes, sir.
Okay. I think, first of all, thank you very much for the organizer providing me such a great opportunity to share my, kind of a bit of knowledge in front of all dignities. And I hope that it will be beneficial to each and everyone uh, attending the workshop. For betterment of this one, can I just, turn off my video so
Sure.
that, yeah, so
Yes,
that we
and
can.
your voice is little bit low, sir. If you can increase.
Okay, okay, okay. I can do that. Yeah. Now it's okay.
Yes, yes.
Yeah,
Yes, now it's okay, sir.
yeah. All right. So basically, we are trying to means basically I am trying to deal with computational luminescence. In this one, maybe we will go for a couple of simulation method used to explain experimental data because I mostly work on experimental stuff rather than theoretical work. But many of the time when I get back to India, I found that people are mostly spending their time just to do emission and excitation data plotting and publishing paper. So I decided to work with Doble sir and to deal with couple of techniques that will be beneficial for local students, so that which I learned in last 3 or 4 years, that can be definitely, if that helpful to new students, it will be my pleasure to to get with that my knowledge. So uh, today's I mostly going to focus to get little bit grip of this workshop. We will discuss a bit of luminescence, how luminescence can occur for those students who are new to this area. Then generally in luminescence we get two kind of spectra. One is sharp and the other one is wide spectra. We will have quick look that how does it differ, because when we talk about explaining those stuff, there are two different theory, completely two different theory is applicable for both type of spectra. Then we will go for general general techniques or different computational methods used in luminescence. And as I said, we cannot go for all stuff. So basically, I will try to focus on one of those theory, Jude-Ophel theory, and if time permits, then we will go for electronic vibrating interacting parameters technique. Let's see how times will shape out. So everybody does know that, means most of the people, because in our region mostly people chemistry and physics, means including material science, are mostly spending their time on learning and doing research on luminescence. So luminescence basically is a phenomena in which body emit light in form of emission when it absorbs certain amount of light, means exciting material, exciting probe, we can say. If it is like exciting material is a light, we call it as a photoluminescence. Basically it is attributed to black body radiation, and the electronic transition or time period is kind of more, we are more interested in visible region, so that we can see and we can enjoy the color obtained in that. So emission of light by substance, generally in this case not emitted due to heat. Basically it is due to cold light. That's why sometimes luminescence is also called as cold radiation. Somewhat we call as a two different types of emission generally we observe. Fluorescence, its time period is quite small. It is in between 10 to the power minus 6 to 10 to the power minus 12 seconds, and it is relatively short persistent. But people are mostly working on phosphorescence, in which the time period of emission is comparably large. and sometimes it is even for it occur for seconds, just in case of long-lasting phosphors. So basic mechanism uh, in luminescence, we can say that absorption in most of the case we call as a excitation graph, and when material get absorbed, we call that material as a phosphor. It absorbs the light because we are talking about photoluminescence. The ions jump from its ground state to the excited state. Excited state, generally when we represent in general level, those ground state and excited state we generally shows only one. But here the singlet states are present, or it splits into several multi-states, and we get the emission characteristics emission for each absorption and for each emission. But sometimes we got it reached highest state, and instead of jumping back to ground state, it's settled in somewhere in between. We can say metastable state. But jumping from highest level to metastable state, sometimes it's a non-radiative. It's we call as an internal conversion, and then ultimately it drop down to the ground state and emit different energy. We call it as a phosphorescence. All this process, there are, is a combination of whole luminescence process is absorption. We call it as a excitation. There are non-radiative radiation or internal crossing or internal conversion, and again jumping back to the ground state. And during this one, we get the emission of light, and we term it as a phosphorescence, and in our case most of the time we call as a photoluminescence emission. So just I said, when in most of the situation when we deal with rare earth dopant ion like U3 positive, Tb3 positive, or sometimes in Dy3 positive, we get the sharp transitions. Means here you can see that these transitions are, there is a full width of maximum is very small. So width is very small. We call this one as a sharp transition. And another spectrum we generally we get where the broadness of these peaks last along several nanometers. Means for this one you can see that it starts here somewhere in between 230 and it lasts up to 430. So that one big broad. And similarly for emission we get somewhere in between 420 and it lasts up to 650. So there where we get the big or wide spectra, that is also where it signifies. The surprisingly, although both phenomena occur and we call it as a luminescence, but the explanation, theoretical explanation, or when you are to compare with the computational data, for the computational data, the both parameter required different theory for different consideration. All right. So any luminescence material required two things. We called it as a host. Host is basically something we call as a provide. Means if we use too much of dopant, the luminescence property get quenched, and we called it as a quenching effect. So we need only some traces of dopant in, and that quench should be embedded in the some crystal structure or some parent material. We called it as a host. So the ideal host or good host, we considered there should be at least four basic stuff should or basic property should be followed by the host. First is the low phonon energy. Low phonon energy generally reduces the non-radiative losses. Means when electron jump from ground state to excited state, it try to come to metastable state without emitting anything, and that emission is completely non-radiative emission. Or if there is some internal conversion or internal energy transfer, if your host is uh, very less sensitive to that, that considered as a good host. Then suitable crystal structure, so that your dopant should accommodate into the structure without actually disturbing the actual crystal structure or crystal lattice. That will happen if we get the one of the host element radii should be comparable of the dopant material. Then it should be high transparency to the emission or absorption light so that it minimize the absorption losses. And last but least, it should be chemical and thermally stable so that its durability increases, and with embedding particle or dopants, it shouldn't change very much. The another important factor in luminescence is the dopant, because whichever emission spectra we see is actually property of dopants. It is not to give or take anything with the host material. So we should have the better dopant and which we will get. So for ideal sharp transition, we will go with in red emission. If you want red emission sharp transition, generally people prefer U3 positive. But at the same time, if you need the broad transition, then people will go for Mn4 positive. So selecting dopant is also very crucial task. So definitely the dopant should have suitable energy level, and that match should be the host and the desired emission. Means if someone from the luminescence, they will know that if they are aiming for red, definitely they won't go to TB, terbium, or they won't go to GD. So selecting host is a very crucial thing. Then high emission efficiency, so that minimal non-radiative losses should happen due to the dopant. Then narrow emission light, as I said, narrow emission light generally provide color purity. The spectra we see that related to U3 positive, that is very fine structure. Generally, such material, such emission, we call it as ideal and very high color purity. And last, again, it should be stable chemically and thermally into the host material. Otherwise, your whole process will waste of time. So to explain this kind of material or stuff, we need some theoretical or computational approaches. So one of these one is the most famous, but actually there are some tricks we will see. That is the differential field theory. And in differential field theory, we generally have two differential field theory. One is time dependent. The another one is time independent. The time independent one, it is generalized differential theory, we generally represent by DFT, and the time dependent differential field theory or differential functional theory, we represent it by TD-DFT. DFT is generally give the calculation for ground state calculation, which give a brief information about its structure, electronic property. But when we consider that the atom jump to the excited state, simple DFT does not explain. When we are to consider DFT, or when we are to study excited spectra, we need TDFT, TD-DFT, time dependent DFT, in which is basically uh, uh, theoretically designed for excited state calculation, in which we can successfully explain absorption and emission spectra. But there are few challenges. DFT generally do not deal with the charge transfer states. Means sometimes in excitation spectra, we observe the broad excitation spectra or absorption peak in UV region. That UV region actually charge transfer either from the host material to charge oxide, dopant oxide, or in few cases like European dope, it is a charge transfer from EU to oxygen or oxygen to EU. So in that one, we observe the very broad spectrum at UV region at smaller wavelength or high energy. This kind of broad peak or broad band is not explained by the time dependent density functional theory. Another theory is molecular dynamics. So molecular dynamics basically you're simulating stuff where you can virtually stimulate uh, luminescence or any kind of conditions or any kind of structure where simulating dynamics and energy transfer can be studied. At the same time, it couple with electronic structure, different electronic structure models. Third approaches is hybrid approaches, which generally combine quantum mechanics and molecular dynamics and try to resolve the or try to understand luminescence property at different level. Then, if you want to take it into multi-scale modeling along with all above like TDFT, DFT, and then molecular dynamics, then electrodynamics can be used to stimulate light emission across different length and time scales. Means if you want to study time dependent luminescence spectra, that time we generally go for a hybrid approaches, that to multi scale modeling, in which you not only able to study at different approaches, but also on time scale we can easily get into it. Then excited state method. So basically it is configurational interaction and coupled cluster method, where you can uh, use your data, you can analyze your data considering interaction between the molecule, and if you consider your sample is in a cluster form, you can couple or increase the size of clusters, and you can see how your property changes. But uh, as luminescence people does know that the very beautiful spectra they observed for rare earth or lanthanide doped ion, and there are a couple of techniques or couple of theory which are exclusively meant for to explain rare earth dopant inorganic phosphors or organic phosphors, and one of them is Jude-Offel theory. You can say that they're the only theory which is dedicated to understand the emission or absorption or excitation of luminescence spectra obtained when we doped rare earth metal ion. So there are many property, many theories. You can see that till this date, there is not any better theory to to go and explain with your experimental data with any other theory. So Jude-Offel theory is one of the considers till this date is one of the best theory. I think it is proposed in 1911, and now after more than 100 years, it is still going on. So it basically calculate transition probabilities and intensity for transitions. So we will see as lecture proceed, we see that how things will calculate or goes with that. Then again, we can say that the computational in computational approach there is another theory where we actually estimate the parameter, and we will try to simulate data, emission data, which should matches to our experimental data, that is electronic vibrational interaction parameter. However, Jude-Offel theory is basically applicable to sharp transition in most of the cases, but electronic vibrational interaction parameter, we also called as EVI parameter, it basically explains the transition intensity and hypersensitive transitions, but it explain or it can be applicable to wide emission and absorption spectra such as obtained from U2 positive, Ce3 positive, sometimes in copper excited element. For that, we go with use with EVI parameter. Now, people will say that there are sometimes we doped transition metal ion. So this instead of these two theories, we will go with crystal fit theory to explain the data obtained from the crystal transition metal ion doped inorganic phosphors. Also, the moving on. So first we will try to focus couple of our time on judo-offel theory. So of course, sorry, I told you like it 1911, but it is 1960. It is proposed by Brian Jude and George Offel. You can see these two persons around it. That is Brian Jude and George Offel. These two guys explain, propose this theory to explain the intensity parameter, uh, emission parameter, emission spectrum obtained from for rarer dope ions. So generally it is used for framework for analyzing lanthanide luminescence, means rare earth ion. So till this date, I haven't seen any research paper. If you came across, please let me know that this theory is applicable to other dopant luminescence property. So basically, it is exclusively deal with rare earth or lanthanide dope luminescence. So basically, it estimates radiative transition probability for 4F4 transitions in lanthanide ions. Those people who have worked in luminescence, even in their first month, they came to know that the material doped with rare earth or lanthanides, the all transitions are 4F4 transition. There is not 5D 4F transition or something else. So because we know that electrons present in lanthanides, a free electron present in F shell, those get excited, return back to jump ground state, and during this transition, all these phenomena and spectrum we discovered or we get. So it's again able to predict emission intensity and branching ratio. We will see what is these things or after some time. So, but keep in mind that predicts emission intensity and branching ratio. So it is also able to determine quantum yields, quantum, we can say that quantum efficiency and lifetimes for the this material or this phosphor. And all these are from your emission spectra. So if you go back and see the research paper, many people have spent their time and time to study EU3 positive dope material, because in UK, U is one of the rarest rare earth which has ionic state as a 3 positive as well as 2 positive, and both are giving a complete different structure. Means if you consider 3 positive emission or excitation spectra, you will get the sharp peaks and in red region, orange to red region. And if you go for U2 positive, in contrast, you get the broad peak, and that too in blue region, green to blue region. So these kind of things you observe uh, same material with different ionic state. But this Judah-Offel theory is basically deal with the sharp stuff, sharp transitions. So if you go back and check research paper, many people have spent their time to study emission and excitation spectra for U3 positive phosphors. We will see, because there are few online softwares are available where you can just put your data in and you will get this parameter calculated. Again, that's why it is simple and effective for lanthanide doped phosphor. So why it is essential means there are few people can say that no, we have emission spectra, we can show the transition and we can get. First, if you add JO in your paper, definitely it's going to increase your impact factor by 2 or 3. because it's not only explain your emission and excitation spectra, it will give the better prediction of transition, better prediction of emission and data, and its application. Means, nowadays people even say that if your certain value is greater than this one, then it can be explained for lasing action, good for bioimaging probe and all. So why it is essential? It should be noted. First one is the predicted emission spectra. With this data, you can simulate or you can explain it intensity ratio and branching ratio, how you get the multiple bits and the intensity of that can be explained. Then calculate a radiative time, compare with the experimental value, and you can go with the calculating your efficiency. Then optimizing luminescent material, tailor omega parameter via host composition. Sometimes it is says that the omega means luminescent intensity parameter. We call it the JO intensity parameter, and it is observed that it is depend on host material. Means you can optimize your luminescent material according to your required application by analyzing with this theory. Then it is really used in real life application. The answer is clearly yes. So Joule-Doppel theory uh, used to design phosphor for LEDs and display. The data we obtained, you can see the concentration dependent. You can use the host and you can vary according to that. You can use it in display and lighting technology. Sometimes it is used in biomedical imaging, analyzing lithium-based probes. So the material you synthesize that can be used as a lanthanide based probe and to study biomedical imaging nowadays. One of the paper I am writing nowadays, that one we saw that these material are very sensitive for antibacterial and antifungal activity, where data is very close to the standard antibiotics. So whether it is used or not, but at this moment it is showing some strong property related to biomedical. So this material can be used for lanthanide based probes, and to study those, this theory is beneficial. This is the first application actually evaluating gain idea and properties, and check that whether laser and amplifier, the material can be used for amplifier. That is simply you can conclude by branching ratio. Then temperature sensing, uh, definitely using this theory, you can apply for lanthanide luminescence thermometry. Then chemical sensing. We know that our samples are uh, famous for photocatalysis phenomena. So photocatalysis phenomena, if you go for, they can detect the uh, material and they can decompose it. So pH and this material you can use to study, to detect particular ions which are hazardous, which are photosensitive, and also sometimes it is used to calculate pH of the material. Then biological sensing, track lanthanide based probes in cells and tissue and to check for that. So this theory is applicable for that. Upconversion material, optimizing lanthanide dope nanoparticles for solar cell and bioimaging. You can do that by using omega. And then enhance NAR harvesting design material to convert NAR to visible UV. So basically, last one applicable to where you get the far emission peak in U3 positive, or when you study ND3 positive material. Uh, there that time we can to use this application there. So basically, Joule-Doppel theory is applicable to rare earths. We know that there are many rare earth material, 15 scandium, yttrium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium. ytterbium, and deuterium. The bold one like PR, ND, SM, EU, DY, TB, ER, YB. They are highly studied rare earth element using this theory, and the most studied material is the European one, where you can see many people. Recently, if you go back and check, only in Scopus database, there are 3 lakh 64 paper on luminescence, and where you can get the more than 1 lakh paper is only on geodophile theory. So to understand this stuff, it is like basically to do. Many times what people do, they will go to online software and just they will upload their data and get the parameter. But most of the time we don't know what that parameter are representing. So this lecture might help you to give physical meaning of the parameter or the number you estimated, as well as the mathematical equation you wrote in your paper using geo theory. Uh, as I said, luminescence happens only in their ionic state, and different ionic state shows, excuse me, different luminescence property. So these elements are optically active, and which make them possible candidate for various optoelectronic and biomedical application, which we have summarized in the last slide. So where you can see that it is from right from lightning LED display to go for biomedical and photocatalysis application. So basically, geotheory is based on the statics, free ion, and single configuration approximation. So generally, we cannot use for moving or what you can say bound ion. At the same time, it configure only single. It is single configuration approximation. We will not mix in it more than one. Then it describes the intensity of lanthanides and actinide transition in solid or solutions. It is not only for solid. If you have data from solution also, then also you can use this theory and describe your emission or excitation intensity. The utility of geotheory is that it provides a theoretical expression for the line strain, and the summation over is known as line strain. It is summation. This approximate solution for geotheory. So basically, it gives you the basic expression for your line strain. So we know that every theory needs some assumption. So in this theory, there are 4 main assumptions. So first one, the states are completely degenerating. Assume an average energy for excited state configuration. Second, the energy demonstrator are equal. The energies of initial and final state. The sum over star fitting J level. Assume all star level within the ground state manifold are equally populated. We consider that. And lastly, the sum over dipole orientation, assuming optically isotropic situation. So these 4 basically isotropic condition we assumption we assume, which are related to their degeneracy, uh, energy dominators, star splitting, and dipole orientation. So considering this one, we will assume that thing is for our sample. So which are useful parameter, or the parameter we can estimate it using this theory? The most important or dominant parameter we calculate is intensity parameters. It is represented omega 4, omega 2, omega 4, and omega 6. These are J value. Fit to experimental absorption or emission spectra. It is used to describe transition probability. Then radiative rates, calculate the using again intensity parameter. We calculate that, we represent eta, the branching ratio. We represent it by beta, predict the emission intensity distribution, and the beta value is kind of tell you their application for amplifiers or lasing action. Then we can calculate radiative lifetime. theoretical, and if you have experimental lifetime value, then we can go for efficiency also. The experimental lifetime means if we have like experimental data, from that also we can calculate means emission data. Not I'm not talking about the experimental time decay data. It is from our emission data or excitation data. Then comparing this one, we can measure with the experimental value, theoretical value. We can calculate the quantum efficiency. At the same time, we can go for this one is not ready to process in from the quantum efficiency less than one. If your sample is going on ready to process or transition, it can't really help. All right, so this from this couple of slides you need not to remember because these are the chemical equation which utilize to explain this theory. So that's why I'm also not going to spend much time. But this equation sometimes if you do not go through it or do not sometimes do not cross your eyes, you will get scared of. That's why I'm added this couple of slides. But I feel that it will be helpful to you. So there are two dominating transition, mostly in U3 positive one that we call a electrical dipole transition and magnetic dipole transition. Magnetic dipole transition generally does not affected the crystal structure around. That's why we consider that one as the standard one, and we will transition emission rate is directly depend on strength of on the dipole, and that can be explained or estimated using this one SMD. Uh, SMD is equal to n cube SMD in vacuum. So basically, the magnetic dipole transition rate in vacuum and is given as 14.65 second inverse, and we consider that one is constant for host material. This transition rate acts as a reference for other electrical dipole transition. The magnetic dipole, as it is not affected to environment around it, this one is we considered as the varying transition of occurred due to electronic dipole transition. Then the most useful equation is the emission intensity parameter. Intensity parameter, which is we calculated for dipole transition, electrical dipole transition, and it is given as omega lambda is equal to dmd mu 1 cube e square v lambda cube will u lambda n 9n cube and n square plus 2 whole square I lambda by I1. This one, if you want, I can give you, there are a couple of paper which are already done with that. Will explain, even by me, 2 or 3 paper where we will get the detailed explanation of this one. But if we go only for that, then today we cannot able to reach to the final that software. That's why I'm just spending minimal time on it. So generally, basically, this constant here, dmd is equal to 9.6 into 10⁻⁻⁶ dV square, and this one I lambda is the integrated intensity we calculated from our emission, and V lambda is generally barycenter's value in Cm inverse. So transition means you can say that it is nearly correlated to the peak intensity of your transition. And if your there is not shift, means your V lambda, this value is same for your all concentration, you can simply claim that there is no shifting in your energy wavelength with increasing concentration, means your sample peak position or concentration independent. So this is small thing which validate your data. So here are 3 omega values: omega 2, omega 4, and omega 6. So omega 2 is the most dominating peak you observed in your most of the rare earth metal ion, and it is directly related to distortion and covalency around the rare earth ion. So whether it tells you whether your structure is symmetric at unsymmetry, how your covalency is related to crystal ions are related attached are bonded to the rare earth ions. So it generally tells you the covalency. Higher the value of omega 2 is, higher the covalency in your structure, lesser the distortion. Omega 4 parameter correspond to stability, rigidity for host matrices as well as long range order. But basically, if omega 2 is greater than omega 4 or omega 4 is greater than omega 2, these both condition you can say that whether distortion is more or the sample is asymmetric or symmetric around the rare earth ion. Omega 3 parameter reflect covalency again and a symmetric nature like omega 2, but in most of the cases omega 6 is very weaker, very hard to observe. But again, this is one of the most important parameter here you can get that. So apart from that, there are like few again parameters you get which are written in the here that equation for radiative transition, cross section stimulation, radiative type, branching ratio, and asymmetry parameter. Generally, this one R is directly confirm that whether your uh, magnetic dipole and asymmetric dipole, electric dipole transitions are symmetric or asymmetric in nature. If the R is greater than one, then orientation around your lanthanides ion, rare earth ions are considered to be asymmetric in nature. Many people say that we can just say, uh, emission spectra and we can claim for that. But this is not happen. Uh, everything you cannot say that, okay, I saw my emission spectra and this value are means asymmetric. The electric dipole transition and magnetic dipole transitions are not intensity is not same means that is asymmetric in nature. All right, but the validate our data with proper theory, you need if you with that the confirmation and application of your parameter is more rock solid and you can say it in a better way, explain in a better way. All right. So there are few online software. One is the Lumpack. If you go with that site and if you send an email to them that you need to license key for that. So there are a couple of videos on that site where you can get the license key and from that you can do your all what you can say the judo offering. You can just simply import your uh, emission and absorption data and you can get your value calculated and along with that you will get many beautiful picture also from this one, but it is a bit hard to explain or hard to deal with that. If we have like more time to go with that we can definitely if we get chance in next few days so we can explore that software also. Second and the most famous software is JOES. It is made by Oma's group, and it is again if you ask them, or I think it is available on internet also that link where you can download it to your software mobile, computer or laptop, and you can import your data and you can get the emission and excitation spectra. But for this one, JOS, ESN, all three, JOES, JOEX, and JOLS are mostly applicable or for U3 transitions only. So basically, but it is very easy to and I think it is almost 7:30, so we have enough time. We will try to see how data will get import in JOLS software and how to deal with that to get the values omega 2 because it is the mathematical equations we saw. If you try to calculate your data using that equation in Excel or any other parameter or any other language program, so it will take ages and those people who are not very used to it mathematics they get scared and that's why many people of us get away from theoretical calculation. But if you master in one of these software, then you have to just input your data, and in couple of seconds you will get all those parameters which we saw big equation in last couple of slides. So JOEX, the specialty of this software, again it is made by Osmas Group, but in JOEX you can get the judo of parameters from U3 positive software, but from the absorption spectra. And lastly, JOLS software, it is again SkyApps one, where first they develop for color purity, CIE, and now they are going to uh, provided the platform to estimate judo of parameter also. So this one you can have in your mind, so that in future if you want to go back and study for your data, you can easily apply. So here from one of my paper, we studied for U3 positive dope with 3 different hosts, calcium boron oxide, calcium aluminate, and strontium silicate chloride. So this parameter we calculated different parameters, and we try to put those together for different U3 positive concentration. Here you can see that your A lambda value is significantly depend on host material, and that means our parameter get changed accordingly. And it is also, you can see that two different transition, the value is quite higher, and for 7F1 it is get overlap for this transition. Second, here beta value is also quite depend on your host material, and for 5D0 to 7F2 transition, the values are higher compared to the 5D0 to 7F1, and it is observed in most of the cases. At the same time, if you see for mu and a barycenter's value, so this is actually good that the barycenter value is not depend on concentration. That means your transition peaks are consistent for different means there is not any shift in your peak position. This one is for cross-sectional area. We plotted in a similar way, and where we can see that the values are concentration dependent, as well as means the host material dependent. And this is the sigma 2, because we got only one peak that time. We do not have 5D0 to 7F4 transition in that data set. That's why we got only omega 2 value. And omega 2 value are, again, we can see that it is dependent on your concentration. And most of the cases it depends for your, host material. So this data actually we published in JMS in 2025 for this one. And we already have published, if you're going to talk specifically, Erkude and is already have published this PL data. And later we found that we can estimate JO, and we get that one. And successfully we managed to get into Scopus Index. I think their impact factor is 2.6 or 2.7, I don't remember. But it got published by JO. All right. So another thing is that this paper I think we work with again Preeti Chaure, Doble sir, and I think I forgot one of name. But here we can see that we have data up to 720 mg. So we can able to calculate omega 2 and omega 4. Here omega 2 is greater than omega 4 in all the cases. Means you can see that the potency is more in for your sample around U3 positive ion. And we can see that omega 4 values is depend on your concentration, and surprisingly it varies. It's not like uniformly depend on, it's either increasing or decreasing, but it is depend. And similarly omega 4 and asymmetric ratio, you can see that it is greater than 1 for all concentration, and it is significantly increases with increasing dopant concentration. So that means asymmetry around U3 positive ions increases. From our emission data, you can say that see that the one of the peak is either from magnetic dipole transition or electronic dipole transitions are varied accordingly. All right. So again, we have calculated for SRAL12019 U3 positive sample. We calculated ready to transition, beta value, and branching ratio and cross section area. And we can see that the cross section is A value is higher for uh, 5D0 to 7F2 transition compared to the this two one. This peak is very weak, so we can get the very minimum value. At the same time, you can see that the beta value is around 23 for 5D0 to 7F1 transition, and on the other hand, it is more than 50% averaging. I'm talking about for 5D0 7F2, and again for this one is very less than 20. So you can say that this phosphor can use for lasing action with this transition or the 615 nanometer wavelength. Now we can make the red laser with this transition or 615 nanometer wavelength. So such kind of conformation you can easily claim using this theory and the parameter you estimated. All right. So again, yeah, Revatkar sir, I forgot about it. So again, we got it published in Optical Material whose impact factor is around 4.7. I think. I recently we used different excitation wavelength and we estimated data for emission. I have not seen that data because it's very time consuming. But we managed to get published in ceramic material with impact factor 5.7 with zero of L theory. So that is kind of things means with so doing some theoretical or estimating some parameter, we can uh, increase the weightage or the reviewer or general started believing our experimental measurement data, which kind of very useful for us. All right. So many people in my last one they asked me how we can take the transition, in our excited state or emission data. So we know that in most of the cases we can easily label them and we can solve. But it is useful to have this sheet while doing this import stuff. So basically, when we talk about 5D07F4, so in most of the cases, that transition lie in between 570 to 585. 5D0 to 7F1 lies in between 585 nanometer to 600 nanometer. 5D0 to 7F2, this is the most of the cases, most dominant one. It is lies in between 610 to 630 nanometer. 5D0 to 7F3, it lies in between 640 to 660 nanometer. And after this one, 5D0 to 7F4, it is the last weakest peak generally we observed for our sample. That is 680 to 710. And then 5D0 to 7F5, somewhere in between 740 and 770. And 5D0 to 7F6 in 810 nanometer to 840. These two are, I think, there are, only few papers where we can see that the people they show this transition. Otherwise, in most of the cases in U3 positive dope material, we will go for only 5D07F4 transition. So we can actually go with that equation. Where is that one? So when you click that link, you will pop up with this window. Actually, this window you can see that we have seen case study for different phosphor. Now we will try to find out the real stuff here. So here you can see that we need omega minimum and maximum value, and here we need another one is n. N is the refractive index. If you have absorption data, you can calculate n value from it and for your different transitions, and you can go with that. But if you don't have this value, so you can simply get it for your sample or for your host from literature, and you can use it. Here you can see that you can calculate CIE, UV, average lifetime, color purity, and GEO, of a parameter for you calculate. So if you just import your data, you can do several calculation easily using this. I think this is one of the good, online platform where you can get your data. But this one is constant for European only. That too European 3 positive, because European 2 positive generally do not give you anything. So what you have to do? You have to just go to choose file and try to locate your data saved in your PC. Try to save it as a DAT file or COC file, and then select. If your data is not smoothen enough, so you can click it on remove background, or if you think that it is very good and smoothen, you can avoid clicking on it. All right, I will leave up to that one. This one data is pretty flat and beautiful. See that. So here you can see the transition, because I explain you DF0 to DF6. But here you can see that there are only 1, 2, and 4, 6 required. Means they do not actually require 0 and F3 and F5. Means you do not require 5D0 to 7F0, 5D0 to 7F3, 5D0 to 7F5. These 3 transitions you do not require. So that's why I gives you the probable rate, because here if you do not provide them, you will not get the data easily. So for 5D07F1, your transition should be somewhere in between 580 to 60. So here we do not have that peak. But if you do not give that software, so sorry, we have that. So your peak is somewhere between here. Then click, go to maximum value. That peak ends here. Click here. Then for 5D0 to 7 F2, that one starts from somewhere in between 610. So this peak, I think, and it's end at 630. So your peak will end at, no, sorry, we have to first select this one, then click on it, and then this. All right. Then your F4. F4 is actually somewhere in between 680. So you do not have that peak. 680 means somewhere. So, but you have to give the value, otherwise this software doesn't work. So whatever value you get here, just avoid it. Don't write it down. And then last one is here. So this software, this one has 761. So it is 8. Then again, this one we do not have. So you can say that is 810 to 840. But I am not going to use 810. Sorry, 810. Where is 810? I am not going to use parameter for this one, because I have any peak. Means if I zoom also, I have peak here 715. I know that, but I do not have peak anywhere here. So this one. So just to explain you, I do not have, do not remember which sample is that one. But to just initiate, I give a value refractive, I consider refractive index 1, and time period, 30,000 microsecond, because it is in microsecond, it is not in millisecond. Otherwise, it is 30 millisecond or somewhere. So that one. Then what I will do, it is, you can easily get it from your time decay data. If you do not have, then it also work. So first we will see with the no value, and then press on calculate. As soon as you press on calculate, you will get the value of this one. This one is your omega 2 value. This is omega 4, omega 6. But I know that I have smaller peak here, but this one is completely vague value, because I have to run it if there is not any value, then this software doesn't run. So I'm not going to mention omega 6 value or anything related to this transition in my research. But here you can see that you will get the omega value, transition probability 8 tau, then center value, then peak position. At the same time, you will get the the delta lambda effective, then cross-sectional area, cross-sectional area effective, and then you get the symmetric parameter. You can see that this is almost equal. That's why your symmetric parameter is less than 1. And you can say that your sample is symmetric around. And now I haven't provided any observed lifetime. That's why I got this one 0. So for this sample, if I remember correctly, it is like 31,000 or 25. That value is there. If I now press this one, I can see my efficiency value is 88%. So see, this is like very easy. That big equation summarized into one small sweet platform, which is available free of cost. You need not to pay single rupees for that. But now the crucial thing is you have to compare this data with the standard data, and where you know that there are not any peaks, you have to omit the data to mention in your research paper. Otherwise, it will be like you are spoiling ethical stuff. So basically, you will get that. You can make the similar table which I showed you, and you can get a good publication with click. All right. So in future also, if you need any help to get if you forget this software running procedure, or if you need data for analyzing your stuff, you can contact me. I think the organizer already have my contact numbers. So you can easily contact me and we can discuss and we can try to sort it out or explain your data. All right. So now moving forward, I know it is going to be like, bunch of information in one night or in couple of hours. But I have to tell you few things which are, I always find a way to discuss with Luminescence Society so that they can improve or they can explain your data in a better condition and get a good publication. So that's why. The another thing is the EVI parameters. We know that stand for electron vibrational interaction parameter. So basically, it is coupling between electronic transition and lattice vibration. We know that in our case, lattice vibration occurred due to phonon. Basically, this interaction influence your spectra, and it's actually broaden it up, and non-relative relaxation also get affected. Ultimately, it affected your luminescence efficiency and quantum yield. So this parameter is calculated by by calculating two different factor. One is Ewing-Rees factor. It is represented by S, and H cross omega, that is we called as a phonon energy. So there are some systematic way to calculate these two, and unfortunately they do not have any easy working platform or software to calculate that. But if you understand the process, and if you spend like couple of days to work on your data, you can easily get good explanation. Let's see. So generally, Hunge's parameter, it generally provide you the strength of electron phonon coupling. There are like 4 different value and 4 coupling condition. If S is equal to 0, no coupling, then your transition is pure electronic transition. If your S is less than 1, then it will be a weak coupling. If it is nearly between 1 to 5, then we can consider the moderate coupling. And electronic and both transitions are okay. Then if it is S greater than coupling 5, we consider it as a strong coupling. Electron phonon coupling is strong, means phonon energy is more dominating. Higher S value, you will get the broad spectral lines, and more non-radiative relaxation compared to the lesser value. It influences luminescence efficiency and ultimately Stokes shift. And another parameter is the phonon energy H cross omega. Generally, it is due to the energy of lattice vibration involved in EVA. How your atoms or atomic, present on the corner or somewhere in the body get attracted or repulsed and produces the phonon energy. That one is responsible. It is completely dependent on host material. It is nothing to related with your dopant. Its energy sometimes vary between 100 to 1000 cm inverse. Higher the value of H cross omega means more efficient non-radiative relaxation at given temperature. Somewhere in our sample, I think it is closer to 700 in most of the cases, but depending on your host material and their properties. So how we are going to calculate this one? So there are few, step by step. So basically, first process is you process your excitation data. Generally, excitation data we get for our sample. It is in nanometers. It is in nanometers. So first we convert that spectra into wave number. We normalize the intensity because intensity is not only depend on your material. It is also depend on amount of material you take or the filters you consider. So that's why we normalize it. We deconvolute them because we got the broad spectra. So at max we use 5 pix deconvolution method. Or if you know that it is cerium, most of the cases there are 2 or 3 peaks, so we will go with that. Then we will identify the lowest energy peak to estimate Stokes shift. Then in second process, again we process, second step we process emission data. So first two steps are same. So we generally get emission data in nanometer. We convert them into wave number. Again normalize it. Then we interpolate it. Interpolate generally provide us better, points to get the data. We deconvolute it. We handle symmetric and unsymmetric fits differently. If your sample is symmetric, then it's a different stick emission spectra. If it is not, then that's a different story. Then in third step, now we had the data of convoluted or deconvoluted emission and excitation spectra in form of wave number. So we can easily calculate Stokes shift, and from Stokes shift and one TDS equation we can calculate S value, that is Hund's ring factor and phonon energy. You can make a one small Excel sheet where you can divide accordingly that. Then in fourth step, we model, emission. We use S and H cross omega value to re-get our emission data, and we try to compare it with our major data. And if it matches easily, then you can say that you will get the better fit, and you can say that the Hume's and H parameter are good for your samples. These parameters are good, and you again go back to your initial state, whether check that S parameter is fitted into that region. You can say claim that whether your host is dominating, your phonon energy is dominating, electronic transition are dominating. All right, so this is one of the small case study. Generally, it is, as I said, is applicable to broad spectra, where you can get that. This one I think C spectra, if I'm not wrong, completely. Oh, U2 positive spectra. So where you get this emission, excitation, this one emission, we normalize it and we convert it into wave number. Repeat it, we'll get the zero value on it, that is zero photon energy. Then we convolute the data. From that data, we will calculate the Stokes shift using this two, and then we will put the parameter and we will just simulate data. Here you can see that this is the experimental emission and this is the dotted one is the red. Red dots are the calculated efficient curve using the estimated values, Hughes parameter and phonon energy using E0, Stokes shift and deconvolution. So we will get the good match, and now we get the good match for different parameter. We can say that we go back and we compare our S value, Hughes or X parameter value with the standard one, and we can see that where it falls. If it is falls in a the Green region, then we can say that whether our phonon transition or phonon energy is dominating or our sample structure is dominating. All right. So this is another from Douglas's work. Uh, nice graph. They took out U2 positive stuff. They plotted it. Then again they converted to wave number, normalize it. They plotted together, and they found that here you can see that the Stokes shifts are there. Higgs parameter you can see that for Li BF6 U2 positive Higgs parameter is 1.2, but for Li to be Na BF6 U2 positive Higgs parameter is 4.3. Means here your transition is dominant, but in this case it is closer to 5, so you can say that the phonon one is more dominating. Similarly, here you have two sides. For two sides, you can calculate two value differently, where this one is different. Again, you can get the phonon energy, where you can see that for higher S value, phonon energy is this is one is in CM inverse. That keep in that mind. All right. So values are CM inverse are less compared to this one. And zero phonon energy you can get it from data anyway. All right. So again, this paper is from Priyanka Boyer from WSL Group, and she published. I think her thesis is completely on EVI. She published in couple of paper in from 2013 to 2016 on this. So quite impressive. All right. So what you can take from today's lecture, you can see that the geotheory. Geotheory predict the transition probabilities in analytes. The in geo key parameters are omega 2, omega 4, and omega 6. Generally, geotheory provide applications in luminescent efficiency, branching ratio, and quantum field. With the help of these parameters, you can say that whether your phosphor can be good for laser design, or you can go for better development, or you can find application accordingly. In summarize about geotheory quantifies basically FF transition. Lambda parameters are the most essential one, which are describe local symmetry and covalency, and crucial for optimizing lanthanide-based optical material. Electronic vibrational interaction parameter was the second topic which we are dealing with, which influences efficiency and spectral set. Here key parameters are Hughes factors and phonon energy. This factor and phonon energy affects non-radiative relaxation, Stokes shift, and radiation operator. Applications are quite similar, phosphor, laser, and lanthanide one, but this one is basically applied for wide spectrum compared to the normal one. Apart from that, in summarize, we can say that this one actually beneficial for understanding optimal spectra, and I think it is a good thing to deal with. I don't know how much I try to convince, but it's a good thing. But the thing is that due to lack of time, and we have to discuss several things, so it is impossible to go with that. But again, I kind of feel that it is one of the good stuff to explain it in a better way. I thank you all for your time and patience. I hope that you will get some better ideas to deal with that. If you have any question, I will try to resolve it. Just let me know.
Thank you very much, Dr. Amol Nande, sir, for insightful and thought-provoking lecture. We now open the floor for questions and discussion. I request participants may raise their hands virtually or type the questions in the chat. We will read them out for the speakers. Participants?
There is one question I can see. Where and how can we compare this data from the software?
Okay, from the software, you get the values. And as I say that values will make sense if you compare it with, standard data. So if you, for example, if you have illuminate host, you can try to find out something, related to your illuminate stuff and some data regarding that, and try to compare with your what you can say, the value you obtain. For example, if your omega value is 1.2 into 10 raised to power 21, and if you find a similar paper in there, then you can claim for that. If your omega value is very high compared to the omega 4, then you can say that it is covalency is dominating and the structure is more asymmetric. Similarly, if your branching ratio beta value is greater than 50, then you can say that that one is more suitable for lasing action. So again, means depending on your need, you have to compare with standard data. Compare with the standard data. Is there any further query?
Excuse me, sir.
Yeah.
Actually, we can use this method to make this Geofield analysis for a given data. Means if we have experimental values, then we can analyze that using this geo analysis. But can we predict the values also using this software, sir?
Yeah, you can use that one. Means see, there are big equations are there. So if you use or tweak with that parameter, you can regenerate your data. Means what we do, we try to get our experimental data and fit it with those equations. But you
Yes,
can
sir.
go in a reverse way. You can use your those equation and generate your data. That is also possible. But again, you should be good with mathematics and your parameters with that to do that. But there is not any software, as far as I know, where you can generate the data just by adding the numbers. So means if you are really interested to simulate your own emission and excitation spectra, then you have to do it by developing your code. Is that
CIO,
helpful?
sir, color codes also we can do with this analysis, sir.
Yeah. Geo is applicable to any rare earth material. And as you know, rare earth means in the softwares are easily available for U3 positive. That's why I went with that. Otherwise, Geo can be utilized to use or explain any rare earth material. Means if you considered ND's emission is in far infrared. So that you
Yes.
can explain. Terbium emission is different. U3 positive, that is red emission, that is SM, that is red, that can be explained. So depending on your need and your dopant, it can be vary. So it is not constant for one, but actually due to some transition conditions. So EU3 positive uh, data can easily explain using this one. That's why I provided those stuff. Otherwise, you can do it with any number.
Sir, one more thing, that JOLS software, is there any methods to install that directly? If we use that link, we can install it, or we need any procedure
It
to
is
install,
online
sir?
platform. If you click on it, it will get open in your browser, and then you can use it. There is not needed any license key or anything.
Okay, okay. Thank you, sir.
Okay.
So I have a
There-
query.
Yeah.
Okay. Um,
Can we study phonons with this software? Whatever you have told.
Phonon energy
Phonons.
means you are talking
Yeah.
about EVI.
Yes, yes, yes.
No, for unfortunately, I never came across such software. So what we did, we made one Excel sheet where we manually entered. We couple of year backs, I was dealing with one of the computer physics student. She developed Python code also, where you can easily import the data. It will do conjugation, deconvolution, and everything. And when you enter the data manually and gives the sample size, it produce the data. But it is like a trivial one. Our project got over, and then I also got lazy, so we never came into iteration, proper iteration method. But manually, you can change the value of phonon, and at only one value, you will get the better data which matches with your emission spectra. So it is like trial and error.
Okay, so because here you said that there is S factor which is included in the calculation, which talks about the electron phonon coupling.
Yeah,
So I thought maybe if we can do only phonon calculations also on this
yeah.
platform.
It is phonon calculation means if you see the S equation means viewing the risk factors, we call it as a. So in that one, you need the most equation is depend on H cross omega, and that H cross omega is nothing but your phonon energy. So if
Exactly.
you vary that one, that S factors changes significantly. So ultimately, it is correlated.
Okay. So we are here. I think we are talking about combination. I mean, a compound. We are talking about. Uh, I just have a query. Are we trying to find out alternative materials for lasers over here? Whatever compounds that you share.
No, no. Actually, we are not trying to find out alternative for laser or anything. But we are main motto is whatever emission data we get. If you go back and check the luminescence paper, people just say that we made this series, we got this transition,
Okay.
and that one. But they are not actually correlating with the theoretical stuff. So basically, these two theory allows you to correlate your experimental data with the theoretical value.
Okay. Fine. Thank you. Thank you, sir. That helps.
You're most welcome.
There is one more question from one of the participant, Dr. Rashmi Deshpande. She is asking, is there any general theory which is applicable to ions other than rare earth, maybe elements?
Yeah, there is if you have dopant from transition metal means like Mn, Cr or Bi. For that one, we use crystal field theory. So crystal field theory generally is for 5D transitions, and again that one is different compared to these two. These two are basically suitable for rarer dopant one, but if your dopants are transition elements, then your theory is different.
Uh, Very nice question. One more from Sarang. Are there any open standard data sets which we can use to compare the software data just to have hands-on experience?
Uh, for one, you have to miss. There are a couple of review papers which talk about the published data for different hosts. But there are like means if your omega value is negative, that doesn't make sense. If your time decay value is negative, that doesn't make sense. If your beta value, which you calculate in percentage, it's supposed to be more than 10. So that one, but there is not any defined one because the transitions, this one is mostly related on EU transition width. So if your peak is very small or less intense, this parameter change significantly. So there are conditions that if your beta is better than that one, if your omega is greater than omega 2, your conclusion or discussion would be different. But there is not like omega value should be that one or omega 4 value should be that one. There is not any such database. But comparison is there. If your value is greater than that one, it can be applicable for just, for example, if beta is greater than 50, that one is good for lasing action. Such kind of data you will get on, this published work.
Okay. One more question from Ashutosh Khade. For this thin film solar cell characterization through PL, shall we use the Judd-Oldfield theory?
Yeah, for Geo, because the recently people, that one is I added for up conversion solar cell. So definitely you can use that one for that layer, for the emission spectra you have got.
Okay. Any more questions, dear participants? Or no worries, the resource person is available in the WhatsApp group as well. If you are going through many more doubts, maybe later on, you can put a question in the WhatsApp group, and resource person, I'm sure, will be happy to address those
Definitely, I will
questions.
happy to answer if I am able to.
Yes, yes. And sure, we'll be also requesting your PPT, sir, to be shared with the participant with your kind permission. If you can send us the
Yeah,
PPT.
definitely. I will, give it to you or madam or wherever you want by tomorrow. But actually, I was working all day today,
Yeah, yeah,
so
sure,
I will
sure.
convert them and I will send it to you.
Yes, yes, yes. And also, okay, I can see one more question. No, no, that's just a thank you message. So I hope many participants have been benefited through your lecture. So if you could just frame out a small assignment also for the participants, just to do the hands-on, whatever they have learned today. So that will be not many much problem, maybe a simple problem statement or single set of data to be generated. That is also sufficient. So if you could do that within 1 or 2 days, that will be also good for the participants to do some hands-on.
Definitely, I will give you one emission data which I have published, means which, or I'm not going to publish such data. I will give you so that you can practice the software, and I will give you couple of picture from which you can calculate Stokes shift and zero phonon energy. That will be I
Yes,
will provide.
yes, yes, that sounds
That's
really
a
great.
brilliant idea, yes, sir. Sir, at least give them 2 assignments. That is what we have decided. So two
What?
sets of data.
Yeah,
Assignments you give, and that is
definitely.
sufficient. Yeah. You can
Yeah,
take
Yes,
your own time. I know you're very
yeah,
busy still. You took out time.
yeah. Means
But
today was
wonderful
like a very long day for me.
session, sir. Yeah.
yes.
Yeah,
And also, before we move towards summarization of the session by our chairperson, I would like to inform some things to our participants. Like many of the participants are complaining that they haven't received the attendance link. However, the mail has been already shooted way before the workshop. Still, if you are not added in the WhatsApp group, the please you can contact directly the flyer persons or directly me or maybe the other persons from IIPT or AACST, and we are daily sending the link to the people. Also, we'll be sharing the videos, the recorded videos of the meetings. Okay, maybe by tomorrow I'll be putting down the link, Google Drive link, so that you can watch the videos, which will be helpful for you to solve some assignments for hands-on practice, and also to give a test at the end of the fifth day. Maybe on Sunday we'll have the test, so that you can have 7 days to go through the videos if you have missed any or if you want to revisit any. Okay. But let me tell you, because the videos are very, very large. They are recordings of some 2 hours lecture. So they are having a very huge storage space requirement. So it takes time for conversion of the videos in the Zoom space and then uploading them in the drive. So still from tomorrow, I will try to put at least the videos of yesterday and today's, and they will not be there forever. So please do take out the time of these 7 days and do watch the videos, take out your notes, handouts, and do attempt the assignments and the test. Right? So that is all from my side. And now I request the chairperson of the day, Dr. Vikrant Ganvir, to please, if he have some questions or maybe directly the summarization of the session. So over to you, Vikrant, sir.
Thank you, Dr. Bhakti. Thank you, Dr. Amol Nande, sir, for an enlightening and comprehensive lecture
my
on
pleasure.
computational luminescence. Your presentation has given us valuable insight into both theoretical
Is it me or the voice is getting
My
broken?
voice is breaking. Yeah, it is breaking.
Okay, Vikrant sir, your voice got
Yes, ma'am.
completely broke out. Can you try once again?
Okay. Now,
No. I think there is some problem with the internet connection from your
am I
side.
audible? Am I
Yes,
audible?
yes, it is audible.
I
Still.
think there is a bandwidth problem.
Hmm.
You may try putting down the video.
Now, am I audible, ma'am?
Yes, it is. Perfect.
Okay, so there was some internet connections. Okay, issue.
Yeah.
Uh, we'll learn about the role of computational luminescence in sustainable energy solutions. The key takeaway is that computational luminescence is not just theoretical tool, it is practical enabler of innovation across physics, chemistry, material science, and biology. It opens new frontiers in technology, healthcare, while contributing to the sustainability. Sir, you also explained from basics of luminescence to the Joule-Opel theory and EVI, and also give the demonstration online on this GOL software. On the behalf of all participants, I sincerely thank Dr. Amol Nande for successful. Thank you, one and all.
Thank you, sir.
Thank you, sir. Thank you, organizer. Thank you.
Thank you so much, Vikrant sir. So I now request to offer a formal
Thank
vote of
you.
thanks. I request Dr. K.G. Bhole sir. First, let me introduce Dr. Bhole, everyone. So Dr. K.G. Bhole sir is associated with University of Mumbai and also IIPT chairperson person for SRC 08 Mumbai chapter. So you are very, very welcome over here, sir. And now I hand over the podium to you for the official vote of thanks.
Thank you, madam. Let me take this opportunity to thank today's speaker, Professor Amol Nande. He started with the theoretical background and then demonstrated one or two softwares which can be used for better understanding or calculation of parameters and verification of methods and so on. Friends, we expect some of the participants to come out with such type of softwares in their as the outcome of their study. That will be the best policy or decision we take today. The speaker also tried to explain the theoretical aspects about various parameters, and these parameters which we calculate during our research methodology or research work. Sometimes it is we come across with the limitations of these softwares. So it is better to find out some limitations of the softwares which we are using and try to develop or try to add some of the parameters to these softwares also. That will be one of the additional aspects we expect from some of the participants. It's not only the resource person who tried, but chairperson has given, chaired the session, and Dr. Vikrant Ganveer, who has summarized the speech, today's lecture in a beautiful way. The nice interaction with the participants by the speaker is also comparable and appreciable. So I must thank on behalf of IAPT as well as Association of all Computer Science Teachers, today's speaker Amol Nande and the chairperson of today's session, Dr. Vikrant Ganveer. Friends, today's workshop is because of the advice and the front running efforts taken by Dr. Abha Khandelwal. I must thank Abhaji at this moment. At the same time, it's very difficult to coordinate the activities with so many participants spread out throughout India. And that job is being done by Dr. Bhakti Patenkar, Madam. Thank you, Madam, on behalf of IAPT as well as Association of All Computer Science Teachers. We must thank the participants, and we expect the participant do not restrict your knowledge, your expertise to what your problem is for the research work or the project, but we expect some of you to be in computer field, develop some simulators, develop some of such type of softwares which will be helpful for the next generation of students. That will be your contribution to the society. So thank you all again, and good night.
Thank you so much, sir. So that is the main motto of having such online workshops, that we are able to connect throughout the India, from different parts of India. Rather than saying Maharashtra, I must say India, because many of the participants and the resource persons are outside Maharashtra. So it's a very nice platform, and all must make maximum use of it. So and this is also one of the platform where we can have networking with the resource persons, or networking with the same research area, same interest people. So I'm happy that the participants are getting much more of it than they expected. And the same amount of participation and attendance I'm expecting for all the days of the workshop. And please do attempt the assignments and the test at the end of the workshop, maybe on Sunday. So that's all from my side. Thank you so much. Thank you everyone for joining. And here we can end the session now with the kind permissions of all the dignitaries.
Yeah.
Just before ending, I have decided to have a snap of the day. Each day I have decided to take a snap so that all can turn on their cameras, and we can have a video or a small snap. So please
Yes.
turn on the cameras. I request all the participants also. Okay, I'll wait for maybe 1 minute more to for cameras to getting on from everyone. Okay. So I'm very happy to see the happy faces after the session. The happiness of getting learn something new, that is triggering the neurons in your brain. New neurons are being generated. So here I ask you to please have a smile on your faces. Just a few more. And the last. Yes. So I'm sure I'll be sharing with you all the photographs as well in the group. Okay. Videos may take time, but photographs can be shared very soon. So thank you so much for your active participation.
It will be displayed on our website.
Yes.
In
Yes.
event gallery.
Yes,
So
yes, sure.
everyone can visit there also. But let the workshop be over. After
Yes,
that, we will put everything, all the reports and pictures will be shared on event gallery of AACST.org.
Yeah, hi.
Thank you.
So, thank you
Goodbye.
everyone,
Namaste.
and have a nice evening ahead. Thank you.
Thank you, sir. Thank you, Bole, sir. Thank you, Amal, sir.
Thank you.
Thank you, Vikrant, sir. Thanks a lot.
Goodbye.
It was a
Thank you.
nice, wonderful session.